Okay, great. Good morning, everybody. So it's our pleasure to have Christian Klos from the University of Bonn here as a speaker. Christian studied physics at the Technical University of Darmstadt some time ago now. And he worked in the lab of Jochen Triesch, and I think you worked on self-organization of the visual system.
Yes, on sequence learning.
On sequence learning. And then in 2007, he joined the group of Raoul Martin Memesheimer, Neural Network Dynamics and Computation at the University of Bonn, for his PhD, which he finished in 2022. And now, since then, he's a postdoctoral fellow. So his research interests are the computational capabilities and dynamic features of neural network models. And he's interested in learning algorithms that lie at the intersection of neuroscience and machine learning. For example, gradient descent learning and spiking neural networks, perturbation-based learning, weight and node perturbation, and learning without weight changes, which is called dynamical learning. And he has published on all of these topics and in high-ranking journals in recent years. And without much further ado, welcome again to the talk of Christian, and we are looking much forward to the talk now. So the stage is yours.
Yeah. First of all, thank you for the invitation and the nice words, William. So I'm quite happy to be here. And yeah, I will talk about how to do gradient descent learning that is both smooth and exact despite having discrete spikes. This is work I did together with and in the lab of Raoul Memesheimer, as Raoul already said. Okay, let me start quite general with a question on why does it actually make sense, or when does it make sense to train spiking neural networks? First of all, from a biological perspective, and maybe the most obvious example is to build models of real networks. So for example, you can train your network on recorded spiking activity, which is nowadays quite prevalent, or you train your model directly on a biologically relevant task, and then afterwards you can analyze how the network behaves and what it does, and use it also to predict what the network is doing. And maybe also you can use it to infer synaptic weights. But it's maybe a question how well this works or not. Okay, another possibility is, or application is to infer learning rules. So you would have like a candidate learning rule and then use it to train your network, and then evaluate your candidate learning rules based on how well they perform and how well they fit the data and how plausible they are. And some example learning rules which have been looked at are, of course, backpropagation, so gradient descent, which might not be the most plausible mechanism. These perturbation-based learning methods where weights are updated only based on local information plus some reward signal that is provided. And of course, then there's Hebbian learning, where this reward signal is also absent. Gradient descent or in particular backpropagation might not be the most biologically plausible algorithm, but it can still serve a purpose there as being a benchmark, because it's usually it works much better than these more biologically plausible learning algorithms like perturbation-based learning. Then there's also another aspect or a big field that makes sense to look at spiking networks and to train them. This comes more from the engineering perspective. So what is shown here, the green curve, shows the total energy consumption by general purpose computing, and its prediction how it will develop throughout the next decades. And currently it is approximately doubling every 3 years, while the world's total energy production is only rising by about 2% per year. So it is likely that at some point, there will be a limit for the energy that is available for computation. So this poses the question if there's maybe other computing paradigms that are much more efficient, which can serve especially in machine learning applications, because these generative AI applications are very energy intensive. And who knows, maybe spiking neural networks can play a role there. And one of these new computing paradigms that people are looking at is neuromorphic computing, right? So quite general term, meaning brain-inspired computing, and also mostly at least event-based computing. And Also, there is quite some dedicated hardware that was already developed for it. For example, this leaky chip. And what you can see here is like some performance plot for the leaky chips for a couple of examples. So on the y-axis is the solution time, and on the x-axis the energy ratio of leaky versus some reference architecture. And especially for recurrent neural networks, it really improves the the energy efficiency by orders of magnitude. Exactly. So yeah, that's like the main or some of the motivations on why it makes sense to look at spiking networks and to train them. And then the question is how to train them. And maybe a good starting point is to look at how people are doing it with rate networks or ANNs. And yeah, maybe a little brief reminder. So people are using, of course, gradient descent mostly to train them. And it works like this. So you have your network, it's parameterized by the weights, and then you can define an error function, which tells you how good your network performs. And then if you're at a certain point in parameter space, you can compute the gradient. And then for learning, you move in the opposite direction of the gradient and yeah, thereby reduce the error. Also, one nice thing about gradient descent is that the gradient can be very efficiently computed, namely via the backpropagation algorithm. I mean, which is just running the network in reverse order once. Okay, one major step that happened in the last 10 years when in the research of ANNs and their training was this development of these residual networks where these skip connections were introduced. So usually you would only have like one layer, and then the output of this layer would be the output of the whole block here. But in residual networks, here these skip connections were introduced so that the output of this whole block is rather the output of the actual layer plus the input. And this helped a lot, and people think why it did help or does help is because it smoothens the error surface. So here on the left, you can see like a cut through the error surface of a very deep neural network, but without these skip connections, and you can see that the error surface is very rugged looking. And in that case, yeah, your gradient doesn't really give you much information about what is the best direction to move to get to the minimum here. And the gradient also only gives you information about how the error surface looks like in a very local environment around your current point in the parameter space. But if you use these skip connections, then you get a much more smoothly looking error surface. And this also then leads to much lower test errors. So for example, here they applied the network on the Sci-Fi 10 data set, and using these skip connections, they could really halve the test error. And this was kind of a general finding that these rugged error surfaces really seem to correlate with poor performance. Okay, now going to spiking networks, and there this ruggedness is seems to be a quite inherent problem. And to see this, let's maybe start by looking at LIF neurons, because most people, at least in neuromorphic computing, look at LIF neurons when they train networks. And yeah, let's start with a simple example. So we have here one LIF neuron. It receives two inputs, and it generates one output spike, which is supposed to lie at a certain target position. And then one can define a loss function, which here I did for which here I used only the quadratic difference, and then perform gradient descent on this loss, right? And then one can plot here the loss function, and let's say we start here at a certain point in the parameter space. And at this point, what the neuron is doing is shown here. So this is the potential of the LIF neuron. It's first at the resting potential, then it receives here an excitatory input. That's the first input, excitatory. It potential rises, crosses the threshold. Output spike is produced, voltage is reset, and then it rises again. And then the inhibitory input arrives, and the voltage decreases a bit. Okay, so here the output spike comes much earlier than it is supposed to be. So now we can compute the gradient of this loss function, and it will tell you that, okay, you should decrease here the first weight, the weight of the first input, so that the rise here is lower and that your that the output spike is shifted to later times. Okay, so what happens then? Okay, one moves along this direction, and then at this point, one is at a point in parameter space where the output spike is really directly before the inhibitory input spike. And again, here the gradient will tell you that you should reduce the input weight of the first input. And if you do this, what happens now is that the voltage does not, so it does not reach the threshold anymore, because now the inhibitory input is arriving earlier and is flipping the sign of the slope of the voltage. So the voltage is not rising anymore, but it changes direction. And the output spike completely disappears then in the middle of the trial. And this then leads here to such jumps in the loss surface, or you can also call this like disruptive spike disappearances. And yeah, then you do not have any output spike anymore. And but we have this T spike in the loss function. So what I did here was to set the T spike simply to the trial duration if there's no output spike generated. So we get here like a completely flat region where there's no output spike generated, and this T spike is always equal to the trial duration. And if you want to compute the gradient then on this loss term, the gradient is 0, because I mean, we already set it to the trial duration, and it doesn't change if we move along here. So that's kind of the second problem which you get here, that some people call the dead neuron problem. Because in networks you can get like multiple neurons that lose all their spikes, and then they are kind of dead and do not contribute to your simulations or to your network anymore. Okay, yeah. So these are like the major problems that can occur with LRF neurons for the simple example. And here's another example which has more practical relevance. It's kind of a distilled problem from a classification task from Thomas and Watney here. And yeah, so this distilled version works like this. So you have like one neuron, which corresponds to an output neuron, receives one input. It's a very strong input, so it spikes very often. And because this is an output neuron, it should produce, at the end, it should produce something like a probability. And to get something like a probability, what was done in this paper was that the spike train here was convolved with a double exponential function. So you get here a continuous output. And then, I mean, this should be a probability, so it's not allowed to be larger than 1. So this convolved spike train is on this sigmoid is applied. And then you get like this curve as an output. Okay, so, and let's say now that this output neuron corresponds to the real or to the correct output. So you would like it to have a very high output probability, and you also would like this probability to be very large throughout the whole trial here. Yeah, in particular, one chooses as a loss, or one can choose as a loss, like the integral of the logarithm of this P of t over the whole duration here. And then one can plot here the loss, and then one can also again perform gradient descent to update here the input weight. And what one would naively expect is, okay, we would like the P to be very high at all times, so we just actually want only as many spikes as possible here. However, what really happens is the opposite, because let's say we start at this point. Then what the gradient tells you, okay, I have already a very high value of P here, but low ones here. So actually would like to have spikes here. And the gradient only knows about the existing spikes. So it will tell you, okay, let's move these spikes to the right. And one can move the spikes to later times by decreasing here the input weight instead of increasing them. So and it's actually really moving in the opposite, in the wrong direction. And at first, also the loss does decrease, but at some point, the spike, this last spike here, that is moved to the right, disappears, as in the previous example, and one gets here this jump in the loss surface, and this continues and continues, and when one uses gradient descent here, what one is really doing is increasing the loss here. So that's really not what one would like to do there. Okay, so there are some solutions, or there is a solution how to cope with this problem in this case. So this is what they did in this paper, and it was to first do the integration of the convolved spike train, and then only afterwards applying the sigmoid. But yeah, in general, this I think tells you that because of this disruptive spike disappearances, you can get problems when you train networks of LRF neurons. Okay, people still do use gradient descent with LRF neurons. And how do they do this? So some people are doing basically what I have shown, computing the exact gradient and then performing gradient descent on these existing spike times. Then you run, for example, in these dead neuron problems, and what people are doing is then to just like increasing all of the weights of all of their inputs, which does work, but it's a really quite unsystematic way. Or people use surrogate gradient descent. Maybe very briefly, how does it work? There you discretize time, and then you get like a step function to compute if there is a spike in this time bin, and but the step function is not differentiable. But to still get a gradient, what people are doing is to replace the step function with a differentiable surrogate for the backpropagation run. So that's like the very brief explanation for how this works. And this does enable the gradient-based addition and removal of spikes, but it also has some problems. So for example, it's not exact because you use the surrogate, and it's also somewhat memory intensive because you really need to store the voltages at all times, not only when there is a spike occurring. And yeah, in both cases, you have the problem that you get these jumps in the loss landscapes, which is quite unlike that you have in rate networks, at least in the modern versions that are used in machine learning. Okay, so our goal was now to study or to see if it's actually possible to do gradient descent that is both smooth and exact in spiking neural networks. First of all, because I mean, it's kind of an intrinsically interesting question, we think, because it would mean that you can get smoothness despite having these discrete spikes via which the neurons interact, and because it has some potential practical advantages like smooth, so for example, that you get smoother training like in ANNs, and because it can provide like a novel solution to this dead neuron problem when using these exact gradients. Okay, so now in the following, I will first show how one can get rid of these disruptive spike disappearances. Then I will show how one can then additionally use these exact spike time-based gradients to also add new spikes, and then at the end I will show some applications. Yeah, okay, so how to get rid of these non-disruptive spikes. So let's maybe first dissect a bit more where these spike disappearances happen and how they happen by looking at an LRF neuron again. It receives one input, and we vary the input weight here. And if the input weight is strong, then the neuron spikes early, and then we decrease it a bit, neuron spikes later, and then at some point you're at this position here where you still reach the threshold, but you do not cross it anymore. And this happens when the sign of the voltage slope flips. So before it was always positive here at the threshold, but at some point, due to a small parameter change, this voltage, the sign of the voltage slope flips, and the voltage really starts to decrease at or near the threshold, which leads to these spike disappearances in the middle of a trial. So here's the spike time as a function of input weight, If you decrease the input weight, at some point, the spike disappears. And this flip of the sign of the voltage slope is a quite general finding, which also holds like in other cases where spikes disappear. So for example, here, your neuron receives one excitatory input and then later an inhibitory one. And now we change the time of the inhibitory input. So if the time of the inhibitory input is late, so there's a dark curve here, then neuron spikes here, and inhibitory input comes here. Then this inhibitory input is moved forward in time, so now it comes here. And if it comes directly before the output spike here, it again flips the sign of the V dot, and it's, prohibits the generation of this output spike. And the spike, like, again, completely disappears here in the middle of the trial. And there's also another way where or how a spike can disappear, and this is not in the middle of the trial, but if it is shifted outside of the trial. And as you will see, this is will become quite important. All right. Okay, so that's how the spikes disappear in the middle of the trial for LRF neurons, and how to avoid them. Well, turns out you can just look at QRF neurons, which are also quite widely used neuron model, and there you have this quadratic nonlinearity on the right-hand side here of the voltage dynamics. And if you plot here the right-hand side as a function of your voltage for zero input current, you get a picture that looks like this. So you have a fixed point, a stable fixed point at the resting potential, and you have an unstable fixed point at what we call here the separatrix potential, which gives you an idea how this neuron behaves. So let's look at what the neuron is doing when it receives one input. So here, one input. Neuron starts at a resting potential, then input is received, voltage rises, and when it is above this separatrix potential, then you get into a regime where the voltage self-amplifies. So if the voltage gets a bit larger, then also your slope gets larger, meaning your voltage gets larger faster, and so on. And in fact, this acceleration of the voltage is so fast that, maybe informally speaking, you really reach infinite voltage in finite time. So you can set your spike time to when your voltage reaches infinite voltage. And also you can set then your reset potential to minus infinity, and still your voltage comes back to your resting potential at some point. Now the difference here, the important difference of the QRF neuron to the LRF neuron is that the voltage slope at the spike time, or let's say directly before one, is guaranteed to be positive and, again, informally speaking, infinitely large at the spike time. And this is always the case when you have here a spike. It's really completely independent of the parameters of your network, of your input weights or times and so on. So you have you're guaranteed that you have a constant positive slope here. This has then important consequences because if you look at the same examples again as for the LRF neuron, but now for the QRF neuron, so QRF neuron receives one input, first a strong one, produces a spike, and then this input weight is reduced. The only thing that happens is that the spike time here is shifted to later times. It cannot disappear anymore. Because if you decrease here the weight a bit, you still get into the self-amplification regime and you still produce a spike. And the only way how you can lose a spike is by shifting them outside of the trial duration. This also holds for this other example where the neuron receives one excitatory input and an inhibitory one. Because now here a dark curve inhibitory input comes late, and now if this inhibitory current is moved to earlier times, it arrives here in a region where the voltage is still high. So you still have this self-amplification and you still can generate this output spike just at later times. So also here, you only lose spikes at the end of a trial. And if you lose spikes at the end of a trial, this is a non-disruptive form of spike disappearances because, after the trial end, nothing happens anymore. So there are also other neurons cannot be affected anymore. And that's why you do not get this disruptiveness. One can show that this holds for arbitrary networks, and also one can show that the spike times of a network of QRF neurons change smoothly. So here these spike time curves are smooth functions of your network parameters. Okay, yeah, so that's like the basic idea how to get rid of these disruptive spike disappearances. And now we can quickly check on how our QRF neuron performs for this original example that we had for the LRF neuron, where you had these jumps in loss surface, and now you really got rid of them. So that's already nice, but what you still have here is this flat region, right? Because you can still lose spikes at the end of a trial, and then you have no output spike anymore, and you get here this flat region, which poses then the question of, how to add then spikes, and preferably we would like to do this via these exact spike time-based gradients. And this is what I will talk about next. So we do this via what we call pseudodynamics. And this works as follows. So we have one QRF neuron receives one input, spikes once, but maybe we would like it to spike more often than once. So let's say 3 times. And what we do then is to extend this trial by what we call here pseudodynamics. And during these pseudodynamics, we set the input current to a constant supra-threshold drive. So this drive is given by 1/4, which guarantees that you have a positive voltage slope. And you have then this additional term, which is a softmax function. So basically a smooth version of the ReLU. And this function is applied on the input current at the end of the trial. And this guarantees that your spikes that are generated here during the pseudodynamics are also a function of this input weight in this case, even if you would not have a spike during these ordinary dynamics. Because, I mean, the spike time here depends on the value of the input current and the starting value here. And if there's no spike here produced during the ordinary dynamics, then it will start here at the resting potential. But because you still have this dependency on the input current at the trial, and you still get a what we call pseudo spike time that depends on the input weight. And with this current, we continue our dynamics until the neuron has spiked sufficiently often. So in this case, in total 3 times. Here what is plotted is the spike times then of these spikes of the neuron as a function of the input weight. And as you can see, they really vary with the input weight, independent of if they are really generated during the ordinary dynamics or if they're generated during the pseudodynamics. And for each input weight, you also get a non-zero gradient. So the gradient of the spike time with respect to the input weight. So in principle, you can use then your gradient descent on your pseudo spikes to move them forwards in time and to get enough spikes during your actual trial. So to really add spikes. So that's like the principal idea on how these pseudodynamics work. They get a bit more complicated if you have multiple layers or more complex network structures. So that's a bit technical now, but I will try to at least explain the gist of it. So here we just added a second neuron to the first one and have the same problem. So the second neuron spikes once, but we would like it to spike more often. We again add this supra-threshold current during these pseudodynamics, but we have this additional term here. And this additional term is kind of an interaction between these 2 neurons. And it consists of this factor here, which is the weight, and this weight is then scaled by this additional factor. And the terms that appear here are, first of all, the time of the first pseudospike of the first neuron here. And then this TP is 1 max is the latest possible time of this first pseudospike of neuron 1. So this fraction here is between 0 and 1. And yeah, why was this introduced? Because of two reasons. First of all, to ensure continuity of the pseudospikes of the second neuron here. Because when a spike of this first neuron here crosses here the trial end, what happens is that your value of the input current of the second neuron jumps, right? Because if you suddenly have a new input here, you get a jump here. You would get a jump in this term, and to compensate that you would need this additional term. I know it's somewhat technical. If you have questions about this, I guess we can talk about this after the talk. The second reason why we introduced this term is to ensure also that the pseudospike time of the second neuron varies with this input weight to the first neuron, even if both neurons are completely silent. So we would like to be able to backpropagate gradients through completely silent layers. And this is ensured via this interaction term. Yeah, so that's kind of the short version of how the pseudodynamics work. Okay, we can plot again the spike time of the second neuron as a function of this input weight to the first neuron, and we see that spike times vary with the input weight, even if they do not occur during the actual trial duration. And we can use then gradient descent to move them to previous times. Gradient in this case is not always continuous. It has these small jumps, and these jumps occur when a spike of this first neuron crosses the trial end. Exactly. Okay. So in summary, maybe what are the important properties of these pseudodynamics? Well, yes, they lead to pseudospike times which are continuous and actually mostly smooth extensions of the ordinary spike times. You can also get complete smoothness with a different construction. And the other important property is that they allow gradients to flow through multiple silent neurons. So you can really revive the silent neurons using exact gradients. And now going back to the original example, you get here now a smooth loss function, and meaning independent of where you start here, you can use gradients to move to your minimum here. Okay, so let's now look at some applications. And maybe before doing so, one kind of a bit technical comment, because this is a bit different to how many people are simulating the networks, because most people are using these time-step-based methods, but what we are using are event-based methods, where instead of iterating over time steps, one iterates over spikes. And then this works as follows. So in each iteration, for each spike, one first determines the neuron that spikes next, and then computes its spike time based on its current state. Then one evolves the state of all other neurons in the network to this next spike time, also again based on their current state, of course. Then in the third step, one transmits then the spike of the spiking neuron to its postsynaptic partners. So in this case, it's just adding the weights to the input currents of the postsynaptic partners of the spiking neuron. And finally, one resets the state of the spiking neuron. It has some advantages and disadvantages compared to the time-step-based methods. One advantage is that you get exact, or let's say almost exact spike times, which makes it very easy to compute the gradients in these networks, because you can just use these auto-differentiation libraries like PyTorch and JAX, and they do this automatically for you. And you do not need to really define your, or you do not need to derive equations for your gradients, which you would need to do if you have a time-step-based simulation. However, it does require you to have closed form solutions for your spike times and for your state equations. So for this expression, you would need an exact solution, and also for these ones. And this puts quite some restrictions on what neuron models you can look at. Yeah, but we use neural models for which you do actually have such solutions. And yeah, let's maybe start by looking at a simple and instructive example. We have here a single QF neuron. It receives a couple of inputs, and we vary the weights and the times of its inputs. And this neuron is supposed to spike at 2 time points. So these are depicted here. But we initialize the neuron or the weights and the time such that the neuron does not actually spike at all during the trial. So here's the spike time as a function of the trials during learning, and we start here with the spike times being only pseudospikes. And here these colored curves are the times of the 2 learned inputs. But then we can apply our method and perform gradient descent on these spike times, and then they are shifted into the trial and to their target positions. So you end up with a neuron that spikes where it's really supposed to spike. And during this whole training period also, your gradient is continuous, which is helpful. One note here. So the gradient here is plotted as a function of the spike time arc length during training. And this arc length is basically the total cumulative change of the output spike times of this neuron. So we did this to zoom into the parts where there are large changes to the output spike times. So here, this portion corresponds to what is happening in this part, and I think this larger part here corresponds to what is, I think, more in this region. Yeah, exactly. That was the first simple example. Then we also apply it to a recurrent neural network where we have 10 neurons, and we learn the spike times of 2 neurons. So they are supposed to spike on this gray points, and learning also works well there here. So we can move the spike times into the trial, and there are no spike disappearances happening here. And they are then shift towards the target times, and learning works well. This is a bit more fun example maybe. And before I start, one comment on the neural model. So it's again QF neuron, but instead of having these exponentially decaying input currents, we have here delta pulse coupling, because this is a bit faster to simulate. And what you see here is how the spikes of this network change during learning, and I hope at the end you can tell what this pattern is supposed to show at the end of learning. As you can see, they're kind of oscillating a bit now. Maybe someone can already tell what it is. Yeah. And so that's how the spike times change of 1 neuron. It's shown here in blue. Right. So that's a network consisting of some observable units, which you can see here, and you have some hidden neurons, which makes the learning easier. So we can learn the spike pattern. Yeah, okay, that took me maybe a bit too long time to create, but okay. Looks nice, I think. Okay, this is a bit more serious example now. It's the final one where we applied our method to MNIST learning. And there we have a 3-layer feed-forward network. And for the input, so we have 1 neuron for each input pixel, and each input neuron spikes then once if the luminosity of this input pixel is above some threshold. And we use then for the output latency coding or time to first spike coding, which means that the first output neuron that spikes is also the prediction of the network. So let's say neuron 1 spikes first, then your model predicts that the input is neuron and that your input is the digit 1. There's some motivation on why to use such kind of coding. There's a biological motivation because if you do, one can show that if one looks at the visual system, that the reaction speed of humans to visual input implies that at least some sensory information is encoded by first spike times, because this reaction speed is so fast that it's only possible for each neuron to spike once in this hierarchy, in the visual hierarchy. There's also motivation coming more from this engineering side or from neuromorphic computing, which is that this time to first spike coding is very energy efficient and fast, of course. So a special thing we did here was that we initialized the network such there were no spikes during the trial duration here. So it's a completely silent 3-layer network, but because of our pseudospikes, we can still backpropagate gradients throughout the whole network and then successfully learn MNIST. And we end up with a network where we have almost no silent or dead neurons, meaning every neuron participates in classification at least for one input. And but still for each input, you get sparse spiking. So only about like 30% of the hidden neurons are active. And you still end up with an accuracy which is comparable to what previous people achieved with a similar network architecture. Okay, to conclude, so we have shown that it is actually possible to do gradient descent that is both smooth and exact in spike neural networks despite having these discrete spikes. And this also includes gradient-based removal and addition of spikes. And this is enabled by neural models whose spikes only disappear at the trial end, which, for example, includes QRF neurons, but doesn't have to be a QRF neuron. The important property is really that you have this positive voltage slope at the threshold. And then, I mean, we looked at some rather simple tasks, but in the future, we'll also look at more complex tasks and compare to surrogate gradient descent learning and LRF neuron. And with that, I would like to thank our lab, neural network dynamics and computations, and especially Raul, who worked with me on this project, and you for listening, of course.